after we solved homogeneous systems, and now we look at a couple of non-homogeneous systems. So here is the homogeneous system we solved earlier. This example, you see we have a matrix involving 3 variables, and with 0 vector on the right-hand side, it's a homogeneous system. And after we worked on the augmented matrix, that is, we reduce the augmented matrix to the reduced echelon form, right? Then we notice it's already reduced, and then we can solve for x1, x2, with x3 being the free variable. Also, I want to remind you that whenever you solve a homogeneous system, you don't have to write the column of 0, because homogeneous system, that column will always stay as 0. So no matter what operation you use, right? So 3 operations. We do replacement or swapping 2 rows, or do a scaling. So no matter which one of the 3 operations, that will not change this column, last column of 0. So you don't have to even include that column whenever you solve a homogeneous system. So here, so as long as you remember that 0 will stay as 0. And after we solve, we write x1, x2, and in terms of the free variable, x3. So then we write our general solution. You see x1, x2, x3, with x3 being the free variable. So that's the part we solved already. Then if we look at the solution carefully, it is just any real number times 511. So yeah, instead of x3, I can use a t if I want to, right? So t is just a free variable. It can be any real number. So we represent a general solution to the system in this form. Also, we can, yeah, so that doesn't matter if you use x3 or t. It's just a name for the free variable. We can also represent it as, okay, we can call it, how do we represent the solution set, or the set of all solutions for the homogeneous system? It is a set that is spanned by the vector 511, because any solution can be written as multiple of this vector. Yeah. So this is the solution set. Yeah, that is spanned by this vector 511. So to solve a non-homogeneous system, so we can consider this example. So let's call so what I do is here I use the same coefficient matrix. The only thing I do is to change the right-hand side. Instead of 0 vector, I make it non-zero vector. So it is becoming a non-homogeneous equation. So the system is still same, well, in the sense that with the same coefficient matrix A. So I'm going to write the matrix, which is 1, -3, -2, 1. I mean this. And A is 0, 1, -1, and that's the A. Same as before. X is the vector of 3 entries. And B is the vector of 2 entries. But this time, it's not a zero vector. If it's zero, it's still homogeneous, right? So I want to work on a non-homogeneous. So suppose one of the two entries is not zero, B. So now I make it 1, 2. So that is the vector on the right-hand side. How do we solve it? So it's just a system of two equations, and we just solve it as we always did, and we can work on this augmented matrix. This is second rule will be, right, for this augmented matrix, and we can do some rule reduce. So how do we reduce? So we notice that first pivot, everything below it already zero, so it's done. So we don't have to worry about that. Then the second pivot, we notice this is 1. Then we can make use of this pivot and eliminate this as we did to the homogeneous equation, right? We did the same. So let's do that again. So we're going to work on this augmented matrix. The only difference is the right-hand side, instead of a 0 column, it is non-zero. So this, we keep the second rule, as is. And now we are going to replace the first rule. Replace the first rule, that is, we want to make this one 0, right? So that means a multiple of the second rule. Let's write second rule. What a multiple? 3. Yeah, we want to multiply the second rule by 3. Yeah, this number 3, multiply second rule, and then add to the first rule to replace the first rule. So the first rule will be replaced. This is a replacement. So let's work on the replacement. That is, multiple of the second rule will be added to the first rule to replace the first rule. So we can get a 0 here instead of -3. So let's do the replacement, and then we get a multiple of 0 add to 1, still 1, and this 1 times the 3 added to -3 is a 0. Now we achieved our purpose. Yeah, then this 1 times this 1 times 3, right? Times 3, add here. So it's a -3, -5. And this times 3, it's a 6. Add 1, it's a 7. So yeah, we got a reduced echelon form. So it's very simple. After this replacement of first rule, we arrived at reduced echelon form. So no matter how many steps you have to do, your goal is to get to the reduced echelon form. So after you arrive at the reduced echelon form, so we can check. So we want to solve for x1 variable, x2 variable. Those are the variables corresponding to the leading entry. So we can write x1. So let's write x1. So you see the first equation is actually that one. Second equation is x2 minus x3 equals 2. So that's the system corresponding to the reduced augmented matrix. So this reduced augmented matrix. Yeah. So this reduced augmented matrix, we are going to further. We need to go further because solution should be a vector. of 3 entries, we need to provide each entry in order to claim it's a solution found. So x1 is what? It is if I add 5x3 both sides of the first equation, so I have this. x2, if I add x3 to both sides of the second equation, that's 2. x3 can be anything because it's a free variable. So now our solution vector is a vector in terms of x3. So you see that x3 is a free variable here. It can be used to generate any solution. That means whenever you give a value to x3, you get a specific vector as a solution vector for the system. But we can also decompose it into 2 parts. The first part is a part involving only x3. The second part does not depend on x3. We can write 720. So you can see the solution vector is just a sum of 2 vectors of this form. So one constant vector, which is a 720. But we recognize the first part, the vector is, in fact, a multiple of 511. That is solution of the corresponding homogeneous system. But of course, if it's solution of homogeneous, it's not solution of this non-homogeneous. So it cannot be. So they differ by this. Solution of non-homogeneous, if you add this vector, and you get a solution of the non-homogeneous. So let's represent now our solution of non-homogeneous in this form, because that shows a structure. It is a sum of 2 vectors. So let's try to recognize our solution for this non-homogeneous system. Again, we have infinitely many solutions because of the free variable, x3. Remember, we could use t. If you want, you can use a t instead of that x3. So that means it can be any real number. So sometimes people want to use a different letter instead of using x3. So it doesn't matter. So if you use x3 or t, it's just a notation, right? Notation for the free variable. So t can be any real number. And the other part is a constant factor. Because t can be anything. When t is 0, we get 0 vector. So that means this constant vector itself is a solution to the non-homogeneous, right? That is a solution corresponding to 0 value for t. So this 720 is a particular solution for the non-homogeneous system. But there are many other solutions. That is, if you add a vector which is multiple of this 511 vector, can still be a solution to the non-homogeneous system. So that just to explain this non-homogeneous system, because of the free variable, we have infinitely many solutions. Not only that, we notice that if we have this a x equals 0, so and I want to use a notation h for the homogeneous solution. So this x h, so with just a subscript means solution for the homogeneous system. And if I currently solve for the same matrix, I have a non-homogeneous, right? Let's use X, simply X. It's a non-homogeneous system. So the only difference is that I have solved homogeneous system. Its general solution is this part. And also, right now, we also solved the non-homogeneous system. Its solution is also this part. You see, it is the corresponding homogeneous solution plus a solution of non-homogeneous, right? I call it particular solution. This particular solution of the non-homogeneous. So it's there is a relationship between solutions of the two systems. So from this example, we see at least if you have solved the corresponding homogeneous system for this, and then you can relate their solutions. So solution of non-homogeneous is a particular solution of non-homogeneous add any solution of the homogeneous. Yeah, so that means as long as you know one solution of this non-homogeneous system, you can find all solutions of this non-homogeneous system. As long as you add, right, a homogeneous or any homogeneous solution. So that's the condition. That means we have to know the corresponding homogeneous system and the general solution of that. So that's the relationship between the two. And I'm going to show you a picture to show you a visualization of the solutions. So what is this? What is that? What is the general solution, right, for each system? So let's look at this concept. So this U can mean the 511, for example. So when you solve a homogeneous system, so this U and of course, for the homogeneous system, we have always a trivial solution. So that dot means the zero vector for X. So that's a zero vector, right, in this three-dimensional system because X is in R3. So I try to show you this zero vector. It is origin. So that's a trivial solution for the homogeneous system. Any homogeneous system has a trivial solution. We know that. That means, okay, so how do I represent general solution? Remember the general solution for our example one, which is homogeneous. It is a free variable 511. So that means, suppose this is a 511 and any multiple of the 511, if this is my vector 511, let's call it U. So this is my vector U, which is same as 511. And the multiple of this vector U will be a solution. So we can describe our solution along this line. That is this U in the U direction can be as twice as long as u or whatever, or negative 1 times u or negative multiple of u. So as long as it's along this line, then that is a solution of the homogeneous system. So this is the geometric meaning. All solutions will be a line passing through u and origin. So, and then vectors. Yeah. So then we see the general solution set. But what is the set of all solutions for non-homogeneous? So this is a non-homogeneous with the same coefficient matrix A. And we know they differ only by a particular solution, right? So suppose the solution we found already, it is, okay, 7 to 0. Suppose that's the solution. So we just draw that x, y, so this is supposed to be that vector. So once you see that vector, then 0, remember the solution of this non-homogeneous system is the t times u, which is the homogeneous solution of the homogeneous. Let's use xh, the solution for the homogeneous system plus a particular solution. So when that means any solution of homogeneous at this particular solution is just another solution of non-homogeneous. Yeah, so we notice that homogeneous, non-homogeneous solution, that's the difference, right? The solution for homogeneous, solution for non-homogeneous, that's the difference. And then we can use solution of homogeneous to represent solution of non-homogeneous. So here is when homogeneous solution is a trivial solution. So if it's 0, then immediately that is a particular solution. So that's what we get here. So you see, when 0 is homogeneous, I add this particular solution, I get this point, which is a non-homogeneous solution. And if your if it's a certain TU, for example, this is also you see, homogeneous solution. Once we get this homogeneous solution, then our non-homogeneous solution will be this plus what? The particular solution, which is that vector, right? Constant vector, 7 to 0, for example, for that example. And then I add this particular solution, and I will get another. This vector will be, this is the another point, right? That shows we can find this point, which is just a line shifted by the vector of p. So if you look at this line, and the vector on this line will be solution to the homogeneous. And a vector along this line, the brown line, will be a solution for the non-homogeneous. Only because we compare the general solutions between the two systems. You see, solution for homogeneous, solution for non-homogeneous. It's a shifted line. Yeah. So the shift is by the vector of p. Yeah, by the vector P. That's the shift. So that's how different when we try to visualize the solutions to the two systems. So we can find any point, right? Means if you pick a point, for example, I will use a different color, pick a point, that is always a certain TU. So I can always map that. So a certain homogeneous solution, add the P to get the non-homogeneous solution. So that's a P plus a certain TU. Yeah. Okay, so this is the two lines to show the relationship between the two systems. So I hope that gives this a visual explanation. So you saw that XH, which is this, right? A line passing through origin. And then the general solution set for non-homogeneous as a line shifted by the particular solution, which is 720. Okay, this is an example with one free variable for both homogeneous and non-homogeneous. Next is an example. We know we solved this earlier in the previous lecture when I talked about homogeneous equations. So we know this system, it is a homogeneous with two free variables because after we reduce the augmented matrix to the reduced echelon form, we notice that we have two free variables. Yeah, so this, for the first equation, we have 1, and then you have free variables, x2, x3. So because of that, we can represent our solution using two free variables because only one constraint, and then x1, yeah, as this in terms of the two free variables, and then we can represent our solution. That means the vector, solution vector of three variables in terms of two variables. So which two are free? We solved x1, right? X1 is in terms of x2, x3. So x2, x3 are free variables. And then we decompose into two parts. So that's the part we did already. So we just want to see, okay, with the two free variables, you have the option to name them differently if you want, right? If you say, okay, I want to just use a different letter because I want to show that S is arbitrary real number, T is any arbitrary real number, right? So just, yeah, it doesn't matter if you change the names. So if you use x2, x3, still they are free variables. So they're just same as the ST. So anyway, so it's another way to represent the general solution. And we see that general solution for the homogeneous system. So let's write for this AX equals 0. And we represent the solution side of this homogeneous system as the set of vectors that are spanned by these two vectors, because any solution is a combination of the two vectors. So once we know the homogeneous solution, I want to solve and for the same matrix, but we revise the problem so that it's a non-homogeneous. So let's look at a non-homogeneous system with some non-zero vector on the right-hand side. So here, the matrix, I will make it the same, A. So after the row reduction, we will still have the same reduced coefficient matrix, but the right-hand side will be different. So the A will be the same. A okay, yes. So 1, -3, -2, and 2, -6, -4. And the B, we will make it 1, 2. Let's compare with the previous system. It's the same coefficient matrix as you can see here. So you see 1, -3, -2, and 2, -6, -4. Yes. So, and previously we solved homogeneous system. Now we're going to solve non-homogeneous system. To make it non-homogeneous, I just invent this problem with B being a vector, which is non-zero vector. So yeah, as long as one of the two entries is non-zero, then it's non-zero vector. So I just pick one vector. So let's solve this system. So here is the problem, right? Given non-homogeneous for you to solve. How do we solve it? Reduce, just like how we did the homogeneous case. We just do the same. So it's do the same. So we just row reduce. So immediately we identify the pivot and then keep the first row as is. So 1, -3, -2, 1, and make this one 0. So I want to reduce the two. So do a replacement. What is the replacement? We need to do the replace the second row. Replace second row. What do we do? So anything add a multiple of the first row, right, will be added to the second row. What multiple? The first row times -2. So this number -2 is the multiple. Yeah. So yeah, so this is what we do. The black fonts are the equation numbers. So the first equation, the multiple of the first equation, which is -2. Multiple, okay, add to 2, then we get 0. And then -2 times -3, we also get 0. -2 times -2, which is +4, adding to -4, also 0. So then -2 times first equation adds the second, also get 0. So now we reduced the non-homogeneous to the reduced row echelon form. The reason is that this is only one pivot, right? Everything else in that column is 0. So reduced. And then we have two free variables. So I can write the equation x1, x2, minus x3 equals 1. That's the equation. Now non-homogeneous. And general solution will involve two free variables. Let's write the general solution. So must remember to provide a solution with 3 entries. So a solution vector must have 3 entries. So then that means x1 is what? From this equation, we can find x1, right? X1 is the variable corresponding to that leading entry. X1 is this, 3x2, 2x3 plus 1. Now, x2 and 3 are free, so I can write a general solution. X2, x3 are free variables, but x1 can be written in terms of x2, x3. So I will know how to calculate x1 as long as I give value to these free variables. So we will have this general solution. Again, so this solution is possibly written as sum of three vectors, because this vector is just a sum of three vectors. One vector involves only x2 free variable, x2. One vector will involve only free variable x3. And one vector will involve only constant. That means does not involve either x2 or x3. So I want to kind of decompose the vector. You see, that's the general solution for the non-homogeneous system. And we can write general solution into a sum of three vectors. So still, the first vector involves only x2, so we can write the first vector as a multiple. Oh, so that's x2. x2 times what vector? 3, 1, 0. And the second is x3 times what vector? 2, 0, 1. The third vector is just 1, 0, 0. Yes, so now we see better the structure is just the linear combination of two vectors plus some constant vector. Yeah, so, and if you go back to the corresponding homogeneous system, 3, 1, 0, 2, 0, 1, look, that is the solution of homogeneous problem. Do we realize that this, right? Solution of the homogeneous. Just realize this homogeneous system with the same coefficient matrix. And we already found general solutions. They are spanned by the two factors. So we recognize that form in the non-homogeneous system. Yeah, so now we can write. So now let me summarize. So this part is just homogeneous solution. Yeah. Recall that we have homogeneous system, and I use the same coefficient matrix. I created a non-homogeneous system, right, with a certain B, non-zero vector B. But these two are related. So in order to differentiate solution to the homogeneous, I use a subscript XH. So that is, this part is solution of homogeneous. But if it's solution of homogeneous, it cannot be solution of non-homogeneous, right? We know that if you substitute this XH, you will make it a 0. You cannot satisfy this. So that means solution of homogeneous is not possibly a solution of non-homogeneous. But it can be used to represent solution of non-homogeneous. So here is X That's my solution of non-homogeneous. It is solution of homogeneous plus a particular solution of non-homogeneous. Why do I say this is a particular solution? This part. Why this one is a particular solution of non-homogeneous? Because when the homogeneous solution is a zero solution, because homogeneous solution always has a trivial right solution case. That means when for example, this possible, this can be, because they're arbitrary, they can be zero as well. So that means when this is the trivial solution for homogeneous system, then automatically this is again still a solution of the non-homogeneous. So just realize that's just a solution, right? With adding all the extra other vectors, still solutions of the non-homogeneous. So now we can see the similar structure as we saw earlier. It's the relationship between solution of homogeneous and solution of non-homogeneous systems. That's the relationship. So they differ by this, a vector E. So in this example, right, we can use this vector 1, 0, 0 to show the relationship. So first, I will show you what is the homogeneous solution for this example. Because of two free variables, then we use the two vector. Yeah, the space spanned by two vector will be, okay, let's see. It's going to be different than this case. So you will see here, it's a trivial solution for the homogeneous system. And if you have two vectors that will span a subspace, it's a plane, right? So that is a plane passing through this origin, because trivial solution is also. So you can extend the plane. That means it's going to be a plane in the R3. So we're trying to show in R3 the solution set for the homogeneous system. So that's this one. And solution set, that means any vector, right, as a linear combination of the two vectors. If you remember the two vectors. So one vector, let's name the two vectors, because it's hard to remember, but I can call it U. I can call this one a V. So when you have U and V, any linear combination of this U, right? This U and this V, then I can say U is 310. V is 201. Yeah. So U and V, an arbitrary combination of the two will be solution of homogeneous. So then you can see that UV will generate this space, because arbitrary linear combination. So any vector in this space will be a linear combination of U and V. So this is a two-dimensional space in R3. It's a plane that is generated by the two vectors UV I just defined. So then we call this solution of this what? XH, because it's a solution to homogeneous system. And then solution of non-homogeneous system will be X. If you add this by this P, which is a particular solution, that vector is actually a particular solution to the non-homogeneous system, because in the special case, when the homogeneous solution is trivial solution, you add that constant, right? We already saw that constant, which is 100, this one. So 100 is the particular solution. So it's just a vector. It's just a vector. So I'm going to show that vector here. So that is this vector, which is a particular solution to non-homogeneous. But there are other vectors. So this particular solution, we can find other particular solutions for the non-homogeneous, as long as you add a homogeneous solution. So that means we see solutions to homogeneous and solutions to the non-homogeneous, and they are two different sets, right? Solution and solutions. They are two different sets, and the two sets do not have common elements, because the solution of homogeneous must add a constant in order to be solution of non-homogeneous. Yeah. So that means the set of non-homogeneous is, in this case, geometric interpretation is all the vectors in here. So shifted by a P, by using the vector P, that's the particular solution. I think we can also use XP in order to say this is the vector which represents a particular solution. We can use XP, means so this vector means a solution vector, right? To the non-homogeneous. So any vector in this will be a solution of non-homogeneous. So actually, that is a vector actually in here. That means, it can be obtained from adding of P to the homogeneous solution to get this vector. So you can visualize the two different sets. Okay, so now we have seen the geometric interpretation to the two solution sets, and the main focus is on the structure of solutions. And how solution sets of the two systems are related when they share the common coefficient matrix A.